uh, very, very fine grained as you get close to it. It's almost like a powder. Ground mass is very fine. I'm going to step off the limb. That's one small step for man, one giant leap for mankind.
Good morning, good afternoon, and good evening to everyone who joins us from around the world. This is Stack Series, and we're so glad you're here.
This is Andrew and Renee, your hosts. We welcome you to the show.
Today, we are exploring the intersection of green chemistry and carbon-negative materials.
It's wonderful to be back. And this topic, it couldn't be more timely. We're really seeing a fundamental reshaping of the entire industrial landscape.
Reshaping how, exactly?
Well, we're moving away from that classic 20th century model, the one that's all about extraction and consumption.
The take, make, waste model.
Exactly. And we're moving towards something that, it more closely resembles a biological cycle. It's a huge shift from just, limiting damage to what we're now calling regenerative engineering.
Regenerative?
Yeah.
That's a heavy word. I think for a long time, the public perception of sustainability, and frankly, a lot of corporate strategy around it, was essentially just harm reduction.
Doing less bad.
Right. Try to use a little less water, try to emit a little less smoke, maybe recycle a few plastic bottles. It was all about doing less bad. But looking at the stack of research we have in front of us today, the ambition has completely shifted.
Completely.
We aren't just talking about neutral footprints anymore. We are talking about materials that actively heal the environment as they're being manufactured.
And that's the core distinction, isn't it? The linear economic model, which, it really kicked into high gear during the Industrial Revolution, is a one-way street.
Take, make, waste.
Take, make, waste. The chemical and construction industries have, historically, been the absolute engines of that model. But the science we're discussing today, it really challenges that fundamental physics. It proposes that the very act of, say, building a skyscraper
or manufacturing a plastic container
could be the mechanism by which we clean the atmosphere.
Which just sounds like a paradox.
Yeah.
We're so conditioned to think of industry as the villain in the climate story. But to understand how industry could possibly become the hero, we have to look at the rule book. This isn't just a bunch of random, disconnected innovations. It's all built on a very specific philosophy.
A framework known as the 12 Principles of Green Chemistry.
Exactly.
Right. And while a lot of people in the field might know the name, I think few realize just how foundational this framework really is. It was developed by Paul Anastas and John Warner way back in 1998.
A long time ago, really.
It was. And it serves as, you could almost say, the constitution for this entire movement. What really stands out to me about their work is that it moved environmentalism from the tailpipe to the drafting table.
Okay. So it's proactive, not reactive.
Precisely. It isn't about cleaning up the mess after the fact. It's about designing the chemistry from the very beginning so the mess never exists in the first place.
And that brings us right to principle number 1. Prevention. The official text it's pretty straightforward. It is better to prevent waste than to treat or clean up waste after it has been created.
Seems obvious, doesn't it?
It does, but in practice, this idea fights against a century of, economic inertia. It's often cheaper, at least initially, to just be messy and then pay a fine or pay for the cleanup later on.
Historically, yes, that was the economic calculation. In the chemical industry, we actually track this using a specific metric. It's called the E factor, developed by Roger Sheldon.
The E factor, what's that measure?
It measures the ratio of the weight of waste produced to the weight of the desired product. Simple as that.
Okay, so a low E factor is good, a high one is bad.
You've got it. In the oil refining industry, for example, the E factor is actually quite low, around, say, 0.1, because they've gotten very good at using every single drop of crude for something.
Right, nothing goes to waste. But when you look at something like fine chemicals or pharmaceuticals,
the numbers get ugly. They really do.
Probably.
In the past, the pharmaceutical industry often operated with E factors anywhere from 25 to, over 100.
Wait, 100?
Yes. That means for every 1 kilogram of an active drug that's produced, you might be generating 100 kilograms of waste.
100 kilograms? Of what?
Waste solvents, failed reagents, byproducts. just chemical garbage.
That is a staggering inefficiency.
Okay.
It's like buying a car and then finding out they threw away 2 other cars worth of steel just to get yours out of the factory.
It's a very fair comparison.
Yeah.
But this is where green chemistry has had a huge impact. By redesigning the synthesis, the actual chemical pathway, you can drop that E factor dramatically.
And this ties directly into another one of the principles, right?
It does. It leads us straight to principle number 2, atom economy.
I've always loved this term because it sounds like a financial audit, but for physics.
And in a way, it is. Barry Tross developed this concept. You see, traditional chemistry for decades focused on one thing, yield.
Did I get the product I wanted?
Exactly. Did I get a lot of it? Atom economy asks a much more profound question. Where did all the atoms go?
But, okay, so it's tracking every single piece.
Every piece. In a perfect reaction, a reaction with 100% atom economy, every single atom in your starting materials ends up incorporated into your final product. There are no leaving groups, no side products, no scraps.
It's like cooking a meal where you use every part of the vegetable, the stems, the leaves, the peel, and you're left with absolutely no scraps for the compost.
That's the perfect analogy. And if we apply this to our topic today, carbon-negative materials, the implications are just massive.
Because if we're using carbon dioxide as a feedstock, as a starting material,
You don't just want it to facilitate the reaction and then float away. You want the carbon atom itself to become a structural component of the final material.
it has to be locked in.
You want that carbon locked into the backbone of the polymer or into the mineral matrix of the concrete. If it just washes away as a byproduct into the water, you haven't really solved the sequestration problem.
You've just moved the carbon from the air to the water.
Precisely. Real atom economy demands that the pollutant becomes the product.
There's another principle that seems to come up again and again in all these breakthroughs we're going to talk about. Principle number 9, catalysis.
Catalysis is the engine of efficiency. It really is. A catalyst, by definition, is a substance that it lowers the activation energy of a reaction without being consumed by it.
Okay, so it makes a reaction easier to start.
Much easier. In traditional industrial chemistry, we often use what are called stoichiometric reagents. These are chemicals that react once and are used up. That generates waste.
Or we just used brute force.
Brute force, high heat and high pressure to just smash molecules together until they did what we wanted.
Which usually implies burning a lot of natural gas or coal to generate all that heat and pressure.
Yeah.
So you're emitting carbon to power the reaction that's supposed to be making your green chemical.
It's a vicious cycle. But with advanced catalysis, and especially the biocatalysts or enzymes we're seeing now, we can run these incredibly complex reactions at ambient temperature and pressure.
Room temperature.
Room temperature. And that directly fulfills Principle 6, design for energy efficiency. If you can make a plastic at room temperature just because you have a brilliant catalyst, you have just severed the link between chemical production and the power plant.
So we have the framework. Prevent waste, use every atom, and use catalysts to lower the energy bill.
That's the core philosophy.
Now we need to parse the vocabulary because the marketing departments have really muddied the waters here. We see low carbon, net zero, carbon neutral, and carbon negative thrown around almost interchangeably.
And they're not interchangeable.
Not at all. And for the engineers and investors listening, those distinctions are legally and physically distinct.
They are, and the confusion is actually dangerous. So let's clarify carbon neutral first. This is essentially a balancing act.
An accounting exercise.
Right. It means that the net greenhouse gas emissions associated with a product or an organization are zero. So if you emit 1 ton of CO2e, that's CO2 equivalent.
You have to sequester 1 ton.
Exactly. Emissions equal sequestration.
But that word sequester is doing a lot of heavy lifting there. For a lot of companies, that just means buying carbon offsets, right?
And that is the heart of the controversy. If I run a dirty factory, but I pay someone to protect a forest in Brazil, am I truly carbon neutral? On paper, maybe. But did I actually change my process? Did I innovate? No.
Right. Carbon negative, however, is a different beast entirely.
A completely different category.
Carbon negative implies that the material itself is an active carbon sink.
It implies active reduction of atmospheric carbon. The production of the material removes more CO2 from the atmosphere than was emitted during its entire supply chain.
The whole thing. Mining, transport, manufacturing.
The whole life cycle. The material leaves the factory having made the atmosphere cleaner than it was before. It's an incredible goal.
I've also heard this called climate positive, which I have to say sounds a bit like a branding spin.
It is mostly marketing, you're right. Carbon negative is the proper scientific term because it refers to the literal mass balance calculation. To achieve this, you have to understand the two different pools of carbon we're dealing with.
Okay, which are
Biogenic and embodied.
biogenic.
Mm.
That's the carbon that biology handles for us, right?
Yes. Plants, algae, cyanobacteria. They all use photosynthesis to pull CO2 out of the air and turn it into biomass. Things like cellulose, lignin, starches.
So if you use that biomass, that plant, to build a wall,
You are effectively taking the carbon that was in the air yesterday and locking it up inside your building for hopefully 100 years.
you have to subtract the embodied carbon.
You always have to subtract the embodied carbon. That's the other side of the ledger. You use diesel to run the tractor that harvested the hemp.
You used electricity to run the saw to cut the panels.
You use fuel to truck those panels to the construction site. All of that is the embodied carbon.
So the equation for carbon negative is simple, but it sounds brutally difficult.
It is. The stored biogenic carbon must be greater than the total embodied carbon. End of story.
And that is a really hard number to hit. You can't just, use a bunch of wood and call it a day if you ship that wood halfway across the world on a dirty freighter ship.
The logistics matter every bit as much as the chemistry.
So let's pivot to where this battle is being fought most fiercely. The built environment. I was looking at the data from the UN Environment Program before the show. The building sector is responsible for roughly 39% of global energy-related carbon emissions.
39%. It's massive.
It is the elephant in the room. You simply cannot solve climate change without solving construction.
You can't.
And the villain of that story, traditionally, is concrete. It's a staggering statistic. If concrete were a country, it would be the third largest emitter in the world.
Right behind China and the US.
Just from one material. It accounts for roughly 8% of all global emissions.
And it's so important to understand why. It's not just the energy used to mix it or pour it. It's the fundamental chemistry of making cement.
Portland cement, specifically.
Yes. To make Portland cement, we take limestone, which is calcium carbonate, and we heat it in a kiln to about 4,450 degrees Celsius.
Which requires an astronomical amount of fossil fuel.
That's the first hit, the energy hit. But the second hit is chemical, and it's unavoidable in the traditional process. When you heat calcium carbonate, it thermally decomposes. It breaks down into calcium oxide, which is the clinker we want, and CO2 gas, which flies straight up the chimney and into the atmosphere.
So even if you could power the kiln with solar energy, you'd still have a massive carbon problem.
A huge one. Roughly 60% of the emissions from cement are from that chemical reaction itself. The rock itself is releasing CO2. You can't engineer your way around that with clean energy alone.
So to fix concrete, you have to fundamentally change the chemistry. You can't just make the old way a little bit more efficient.
That's right.
And this brings us to some really fascinating work being done at Northwestern University in a partnership with the cement giant Cemex. They're looking at marine biology.
They are, which seems like an odd place to look for a solution to concrete. But they asked a very simple, very powerful question. How do coral reefs and mollusks build their shells?
They don't have kilns.
They don't have kilns. They don't burn coal. They build these massive, incredibly durable calcium carbonate structures at ambient ocean temperatures, using only the dissolved minerals around them.
So the team at Northwestern figured out a way to mimic this process using electrolysis.
They did. They used seawater, electricity, and dissolved CO2. By applying a very specific electrical current through the water, they changed the pH right near the surface of the electrode. This change triggers the minerals calcium and magnesium to precipitate out of the solution.
They just fall out of the water.
They precipitate and form a solid. They essentially grow a sand-like material made of calcium carbonate and magnesium hydroxide.
The obvious catch here, though, is the electricity. Electrolysis isn't free. It takes a lot of power.
No, it is absolutely energy intensive. But, and this is the critical difference, unlike the chemical release of CO2 from heating limestone, this process consumes CO2 from the water. And if the electricity grid that's powering the electrolysis is renewable,
Wind, solar, hydro.
then you have a truly carbon-negative pathway. You are turning renewable electricity and waste gas into solid rock.
And it effectively bypasses the need for mining sand, which is a whole other ecological crisis we rarely talk about.
Yeah.
And it eliminates the kiln entirely.
It's a really beautiful example of biomimicry. But there are other approaches that are focused more on industrial waste streams. A company called Carbocrete, based in Canada, is attacking the problem by just removing the cement entirely.
Cement-free concrete, that sounds like. Like flour-free bread. What's the binder? What holds it all together?
They use steel slag.
Slag.
Slag is the stony waste matter that's separated from metals during the smelting of ore. It's usually a nuisance, a huge industrial waste product that piles up.
Okay, so they're upcycling?
They are. Carbocrete grinds the slag down and mixes it with aggregate, just like normal concrete. But the real twist is in the curing process. Traditional concrete cures with heat and water. Carbocrete cures their blocks in a sealed chamber that's injected with captured CO2.
So they're literally forcing CO2 gas into the block.
Yes, and the CO2 reacts with the calcium that's present in the slag, and it forms calcium carbonates, it mineralizes. That reaction is what solidifies the block and gives it its strength.
So you're using an industrial waste product, the slag.
Right.
You're avoiding the high-carbon cement entirely.
Yes.
And you're permanently sequestering CO2 in the final product.
It's a triple win.
I have to ask about the scalability here, though. Steel slag is available, sure, but is there enough of it to replace the billions of tons of cement we use every single year?
And that is the bottleneck? The honest answer is no. We produce about 4 billion tons of cement a year globally. The supply of high-quality steel slag is a tiny fraction of that.
So it's a great niche solution, but not a global one.
It's a fantastic solution for the markets where that slag is readily available. It's a very important piece of the puzzle, but it can't be the whole picture.
Okay, so then we have other companies taking a more biological route again. Prometheus Materials, for instance. They're using microalgae.
Specifically, a type called coccolithophores. These are microscopic algae that naturally produce these intricate shell-like armor plates made of calcium carbonate.
So Prometheus is effectively growing biocement.
That's the idea. They cultivate these algae in large bioreactors. The algae capture CO2 from the air through photosynthesis to grow, and then that biomass, rich in calcium carbonate, is used to bind aggregate together into blocks.
The advantage here, it seems to me, would be thermal performance.
It would. Living materials, or materials derived directly from biology, often have much better insulation properties than dense dead rock. But the challenge for Prometheus is speed. Biology works at its own pace.
Right. Can you grow algae fast enough to keep up with a construction boom in, say, Shanghai?
That's the engineering hurdle. They are using advanced bioreactors to accelerate the growth cycle, but matching the sheer output speed of a traditional cement plant is a very significant challenge.
Let's shift geographies for a moment to India. There's a company called Green Gems that's tackling both the construction emissions problem and a local air quality crisis. This one really resonated with me because it addresses a very visible seasonal problem: crop burning.
Ah, the 5th season in Delhi, the smoke season. After the harvest, farmers often burn the stubble from rice and cotton harvests because it's the fastest, cheapest way to clear the fields for the next planting.
And it chokes the cities.
It does. So Green Gems developed a material they call agrocrete. They take that agricultural residue, the paddy straw, the cotton stalks, everything that would have been burned, and they use it as the aggregate in a building block.
And what do they use to bind it?
They have a proprietary material they call BNDR. It's a zero-clinker, alkali-activated geopolymer. But the real genius is in the life cycle analysis. The plants absorbed carbon while they were growing.
And instead of releasing all that carbon back into the atmosphere in a huge puff of smoke,
It gets locked into the wall of a building.
and because it's made of straw and stalks, I imagine the insulation value is massive.
It's about 3.5 times higher than a traditional clay brick. And in a hot climate like India, that translates directly to lower air conditioning costs over the life of the building. So it lowers the embodied carbon and the operational carbon.
It's a truly systemic intervention. We see a similar philosophy with a company in the U.S. called Plant, but they're using a specific type of perennial grass to replace wood panels.
Right. The logic here is all about the growth rate. A pine tree might take 15 to 20 years to reach harvest maturity. This perennial grass they use can be harvested annually, sometimes even twice a year.
So it's sucking up carbon much faster.
Much faster per acre. It pumps carbon into its biomass and, importantly, its root systems much more rapidly than a forest can. Plant then takes that harvested grass and turns it into structural panels that can compete with things like OSB or oriented strand board.
It's basically carbon farming. You grow your building materials.
It is. And because the grass regrows from the same root system year after year, you don't have to till the soil. That protects the soil carbon, which is another huge reservoir we need to preserve. It's a very clever application of Principle 7, use of renewable feedstocks.
Okay, moving beyond these hard materials, I want to get into the realm of synthetic biology. This is where it feels like we stop simply using nature and we start actively hacking it. The work coming out of the Reform Project at Northwestern and Stanford is, well, the only way to describe it is that it's defying nature.
That is not an exaggeration. The project, led by researchers like Michael Jewett and Karen McCann, created what they call an artificial metabolism.
Okay, so for the non-biologists listening, why is an artificial metabolism necessary? Doesn't nature already consume CO2 perfectly well?
It does, but nature is often very inefficient from an industrial standpoint. Evolution selects for survival and reproduction, not for maximizing the production of, say, acetyl-CoA for making plastics.
So there's no natural bug we can use for this.
There is actually no natural enzyme known in any organism that directly converts formate, which we can make very easily from CO2 into the key building blocks that we need for industrial chemistry. Nature takes a very long, winding, inefficient road. The Reform team wanted to build a direct highway.
So they built a chemical pathway that doesn't exist anywhere in the natural world.
They did. They screened thousands of different enzyme variants from all over nature, and then they stitched them together in a novel sequence. But the key innovation here is that they did this in what's called a cell-freeze system.
This is your analogy from earlier. This is taking the engine out of the car.
Exactly. A living bacterial cell is incredibly busy. It's doing a million things at once, repairing its DNA, maintaining its cell wall, dividing, fighting off viruses. All of that consumes a huge amount of energy.
It's overhead.
It's biological overhead. By breaking the cell open and just using the specific enzymes you want in a kind of chemical soup, you strip away all of that overhead. You also remove the toxicity limits. Sometimes the very chemical you want to make is poisonous to the cell that makes it.
The enzymes don't care.
In a cell-free system, the enzymes don't care. They just keep working.
So they managed to convert CO2 into formate, and then their artificial pathway turned that into acetyl-CoA. Why is acetyl-CoA the holy grail here?
Because acetyl-CoA is the universal hub of metabolism. It's the central crossroads. Once you have a cheap, sustainable source of acetyl-CoA, you can, in theory, synthesize almost anything.
Bioplastics, biofuels.
Pharmaceutical precursors, specialty chemicals. It opens the door to making incredibly complex, high-value, carbon-based products directly from captured CO2.
But I've heard that cell-free systems are notoriously unstable. The enzymes degrade quickly, don't they?
They do, and that is the major hurdle for commercialization. Keeping that soup of enzymes active for long periods of time in a large industrial reactor is both difficult and expensive. But the proof of concept is revolutionary. It implies we can decouple carbon fixation from the limitations of life itself.
Meanwhile, other companies like Mango Materials are perfectly happy to use living bacteria, specifically something called methanotrophs.
Yes, methanotrophs are bacteria that, as the name implies, eat methane. This is crucial because methane is a potent greenhouse gas. It has a global warming potential, or GWP, that's nearly 30 to 80 times higher than CO2 over the short term.
So getting rid of methane is a high-impact strategy.
A very high-impact strategy. So Mango Materials strategically sets up its operations right next to things like wastewater treatment plants or landfills, which are major emitters of methane.
The bacteria just eat the waste gas.
Yeah.
And then what happens?
They eat the methane, and as part of their metabolic process, they produce a biopolymer called PHA, polyhydroxyalkanoate. It accumulates inside the bacterial cell wall. It's essentially bacterial fat, a way for them to store energy. But when you harvest the bacteria and extract that PHA, it acts just like a thermoplastic.
So you can melt it down and mold it.
You can mold it, you can spin it into fiber, you can make bottle caps, packaging, all sorts of things.
And the kicker here, I assume, is that it's biodegradable.
Truly biodegradable. Even in anaerobic environments like a landfill or in marine environments, if a PHA bottle ends up in the ocean, other bacteria in the water recognize it as food and they just eat it.
The challenge then must be the economics.
Again, it comes down to cost. Polypropylene, the standard fossil fuel-based plastic, is incredibly cheap to produce. PHA is currently more expensive because of the energy needed for the fermentation and especially the extraction process.
You have to break all those bacteria open to get the plastic out.
You do. So the whole battle right now is bringing that cost curve down to a point where it can compete with oil.
Which might get easier as things like carbon taxes come into play.
Correct. As soon as there's a real price on carbon, the economics of processes like this might tilt very quickly in Mango's favor.
Let's touch on the textile side of things for a moment. There's a company called Ruby Laboratories, and they call their process symbiotic manufacturing. What does that mean?
What Ruby is doing is using a cell-free enzymatic process, much like the Reform Project. but their goal is to turn captured CO2 directly into cellulose pulp.
Cellulose, the stuff that makes up cotton and trees.
Exactly. This is a direct challenge to the traditional cotton industry and the wood pulp industry, which produces viscose and rayon.
And cotton is a notoriously thirsty crop.
Incredibly thirsty and very land-intensive. Ruby claims their process is completely water and land neutral. They are envisioning a future where you bolt their bioreactors onto the smokestacks of existing factories, capture the waste CO2, and spin it directly into yarn.
So you could decouple the fashion industry from agriculture.
That's the dream. You would no longer be fighting for arable land to grow your shirt.
It's an amazing convergence. We have biology, chemistry, and engineering all working together. But we also have to talk about a more brute force approach, direct air capture, or DAC. Usually this conjures up images of those giant farms of fans in Iceland or Texas, just sucking huge volumes of air through chemical filters.
And it's very expensive. The concentration of CO2 in the ambient air is only about 420 parts per million. That's a tiny fraction. Thermodynamically, separating that out takes a colossal amount of energy.
But researchers at Harvard are working on something called photobases to try and change that energy equation.
They are. This is solar-powered chemistry, but not in the way you might think. It's not photovoltaic.
So it's not just a solar panel powering a fan.
No. They found a class of organic molecules that change their chemical properties, specifically their ability to bind with protons when they are hit with light of a specific wavelength.
How does that help capture CO2?
Well, when you shine a light on them, they can grab a CO2 molecule from the air. Then when you turn the light off or change the wavelength of the light, they release the CO2 in a pure stream.
So instead of using massive temperature or pressure swings to capture and release the gas, which is the big energy hog in traditional deity, you just toggle a light switch.
In theory, yes. It could allow for day systems that are powered directly and passively by sunlight, which would drastically reduce the operational cost and complexity.
And then on the complete other end of the complexity spectrum, we have something called mechanochemistry. This feels like a throwback, like brute force, but it's actually incredibly elegant.
It's elegant because it's so simple. Its main goal is to remove the solvent. In most traditional chemical synthesis, you have to dissolve your reactants in a liquid.
And those liquids are often nasty, toxic, volatile organic solvent.
They are. So you mix everything in the solvent, run the reaction, and then you have to use more energy to distill the solvent out, and then you have to figure out how to safely dispose of the waste solvent. It's a huge source of waste.
Mechanochemistry just says, forget all that, just smash them together.
Pretty much. You put the reactant powders into a ball mill, which is basically a rotating drum filled with hard steel or ceramic balls. The kinetic energy of the balls crashing into the powder generates intense, localized heat and pressure. It literally breaks chemical bonds and forces the atoms to rearrange.
It sounds like just grinding rocks, but you're saying it can perform high-precision chemistry.
Surprisingly, yes. You can make very pure compounds this way, with almost no waste. It scores incredibly high on Green Chemistry Principle 5, safe for solvents and auxiliaries, because there are no solvents.
What's the limitation?
The limitation currently is batch size and continuous processing. It's hard to scale up a ball mill to produce 1 million tons of a material continuously. It's much better suited right now for high-value, smaller volume materials like pharmaceuticals.
Okay. We have covered just a dizzying array of technologies, from electric seawater and methane-eating bacteria to solar-powered chemistry and just smashing things in mill. But I want to pause here and put my skeptic hat on for a minute.
Please do.
I walked down the aisle of a grocery store or a hardware store today, and almost everything has a green leaf on it. It says eco-friendly, sustainable, green. How do we, as consumers or investors, know that any of this is real? How do we avoid the greenwashing trap, where a company just buys a few cheap offsets and then claims they're saving the world?
That is the most critical question facing this entire field. Innovation without verification is just marketing. It's meaningless.
So what's the solution?
Fortunately, the era of the Wild West in green claims is rapidly coming to an end. The year 2026 is shaping up to be a real watershed year for regulation, particularly coming out of the European Union.
You're talking about the Green Claims Directive.
Exactly. The EU is effectively moving to ban generic, unsubstantiated terms like climate neutral or eco-friendly unless they're backed up by rigorous, standardized, third-party verified data. And the backbone of all that data is the ISO standards.
Let's break some of these down. The gold standard for this seems to be ISO 14040 and 14044.
Right. Those two standards together define the framework for conducting a life cycle assessment, or an LCA.
A cradle-to-grave analysis.
That's the goal. An LCA forces a company to account for the environmental impact of everything. The mining of the raw materials, the energy used for transport, the manufacturing process, the packaging, the product's use phase, and its end-of-life disposal or recycling.
And the boundary of that LCA really matters, doesn't it?
It is the most important part. A company might try to show you a cradle-to-gate LCA that measures the footprint from the mine up to the factory gate. It can look great, but it conveniently ignores what happens when the product is used for 30 years or when it's thrown in a landfill.
So you need to see the whole picture.
A true cradle-to-grave, or even better, a cradle-to-cradle analysis is the only way to reveal the hidden costs and benefits.
Then there's ISO 146-6 and 7, which is more specific.
That is the specific, dedicated standard for the carbon footprint of products. It provides the detailed methodology for doing the math we discussed earlier, subtracting the biogenic sequestration from the embodied emissions. It ensures that when Company A says 1 kilogram of CO2, it means the exact same thing as when Company B says it. It creates a level playing field.
And for the building industry specifically, we have EPDs.
Environmental Product Declarations, which are governed by ISO 14025. You should think of an EPD as a standardized nutrition label, but for a building material. It lists the global warming potential, ozone depletion, water use, everything.
And architects are starting to demand these.
They are. If you want your steel or your concrete or your insulation to be used in a modern green certified building, you need to provide a verified EPD. You can't just take the salesman's word for it anymore. The data has to be there.
This shift to mandatory standardized reporting feels like it fundamentally changes the risk profile for companies. It's not just about good PR anymore, it's becoming about legal and financial liability.
Absolutely. In many jurisdictions now, company directors can face personal liability for misleading investors about environmental risks or for making false green claims. The greenwashing risk is no longer just a reputational risk, it's a hard financial risk.
So bringing this all together, where does this leave us? We've looked at the philosophy of green chemistry, the amazing innovations in chemistry and biology, and now the legal framework that's being built to verify it all. It seems like all the pieces are there for a revolution, but the assembly isn't quite complete yet.
I think that's a perfect way to put it. We are in the deployment phase. The fundamental science for many of these technologies is largely proven. We know we can make carbon-negative concrete from slag. We know bacteria can make plastic from methane. The challenge now is what the startup world calls the valley of death.
Sealing up.
Scaling from a small pilot plant to a global industry. That journey requires massive capital investment, and it requires customers, governments, large corporations to be willing to pay a green premium in the short term to help these new technologies ride down the cost curve.
But the destination, a world where our buildings and our products are actually healing the atmosphere, at least that destination is visible now. It's not science fiction.
It is visible. We are moving from a paradigm of doing less harm to one of being actively regenerative.
Yeah.
And for all the bad news we hear about the climate, that is a profoundly hopeful place to be.
It really is. It suggests that technology doesn't have to be the enemy of nature. It can actually be its most powerful partner.
That is the ultimate promise of green chemistry.
Before we wrap up, a heartfelt thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support.
And to our listeners, thank you for being part of this journey with us. If you enjoyed today's episode, be sure to subscribe and follow Stack Studios for more informative content, and support us in Patreon.
Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.